So today we're continuing with the discussion we had last time. Last time what we did was we proved that Gauss's law has two different forms, okay? And one we learned about last time was that the divergence of the vector field, the electric field, is equal to the charge density divided by epsilon. And if you're in a vacuum, it's epsilon naught. If it's not a vacuum, epsilon is just some other number. We derived how this worked, right? Gauss's law. And we want to do the same thing now for Ampere's law, okay? To remind you what Ampere's law states, Ampere's law states basically that if you have the integral of the magnetic field around some loop is equal to mu naught multiplied by the current that's enclosed by the loop that you traverse, plus there's another term that we put in here, which is mu naught times epsilon naught times the time derivative of the electric flux. Okay, that's the differential form, or the integral form of Ampere's law. And what we want to do is we want to take this and we want to put it into a different form. We want to use the curl. So the way that we're going to go about doing this is we're going to take we're going to take a coordinate system, like a three-dimensional coordinate system. Like that. And then we're going to say, suppose that in some region of space, I have a magnetic field, okay, within this region, and an electric field possibly too. And within this region, there is a vector field, B, that is a function of x, y, and z. So at every single point in this space, like maybe you come over here, you say, what's the value of B at that location? You say, well, it has three components, and maybe at this location the magnetic field's like this. And maybe at this location over here the magnetic field's like this, and over here the magnetic field looks like this, or something like that. Basically, you've got some magnetic field, and it varies throughout this space in some way, okay? Now I'm going to erase all these values, but that's what a vector field is, right? At every location in this coordinate plane, whether you're back here on the negative z-axis, or you're over here on the positive z-axis, or something like that, at every location within this space, you have a vector that denotes what the magnetic field is, okay? That's what a vector field is, right? Now, let's just know that that's the case, right? And, oops, that's not what I meant to do. Just want to erase these guys. And now what we need to do is we need to basically evaluate this quantity right here. We need to evaluate what this is within this space, okay? So what I'm going to do is I'm going to draw a little box here that's going to represent my loop. Nope, that didn't do it, did it? Shapes, purple, shapes, box. There we go. And just within this box, I'm going to erase some of the things. Why doesn't it? I'm going to erase some of the stuff in here just so that we have a little bit of something to see. So this is going to be our path for the integral that we want to do here. That's the path. And I'm going to say that, we're going to traverse this path in a circle. So we're going to go around this path like this, like this, like this, like this, not a circle, but a loop, right? And we're going to say, on each of these sides, there's going to be different values for the magnetic field. And so on the left-hand side, what I'm going to say is that the magnetic field over here, I'm going to call it equal to B sub y. That is to say, the y component of the magnetic field is all I'm going to care about on this side over here. Over here, I'm going to call the size of the magnetic field by prime. And the size of my loop is going to be such that that's just the value basically at a point in space, because what I'm going to do here is I'm going to say that the length of this side over here is going to be dx, and the length of this side over here is going to be dy. Okay? So dx is the whole length here, from there all the way over to there, and dy is the entire length of what you call maybe the height of this rectangle, right? So it's a rectangle that has size dx and dy, and I tell you that on the left side of this rectangle, the value of the magnetic field is by, and on the right side of the rectangle, I tell you that the value is by prime. Okay? And then on the top, we're going to say, all we're going to care about on this top side here is what the value of the magnetic field x component is going to be. So I'm going to say up here, you're going to have bx prime, and down here we're going to say the value of the magnetic field is bx. Okay? Since the magnetic field is a function of x, y, and z, that means it has components b sub x I hat plus b sub y j hat plus b sub z k hat, and it should become pretty obvious in a second why I'm only going to care about these right here. Right? And our goal now is to evaluate that integral that I underlined right there. That is to say, we want to evaluate effectively summing up the value of the magnetic field dot ds around our loop right here. And I would say that what it's going to be, where do we want to start? Let's start right here. We're going to start right here on our loop, and we're going to go around in a circle, and we're going to evaluate b dot ds. Okay? Keeping in mind, s is like the path length, so I would say that s is like a element of the path length. ds, like that. In fact, its reality is, because this is a dx side, it's really going to be the entire side right here. Okay, but ds is basically an element of the path that you're undergoing here. Does that make sense? Can I give you another example of where this came from? Let's remember what we used Ampere's law for in the past, right? What we did in the past was we said, suppose that I've got a situation where I have a current carrying wire, right? And I say that there's a current carrying wire and it carries current coming out towards you. Current, right? Current, right? We said that we can evaluate what, let's use the same colors. In fact, let's use a circle too. So I take a circle, right? And I draw a circle around this guy. Like that. And I say, okay, this is my path now. It's not a real thing, it's just a path in space around which you're going to do a calculation. The calculation that you want to do is written right there. So around this path, you say, I can break up my path into a bunch of tiny little elements, right? ds this way, and then another ds this way, and then another ds right here, and right here. I'm being really, really repetitive here because I want you to kind of like pick up on exactly what we're doing. This entire path can be composed of a bunch of little tiny, we call line elements, right? It's a circular path, but every one of those things is its own little ds, right? It's an incremental change of the arc length, right? An incremental change d theta of the angle, which leads to an incremental change of your steps around the path. ds could literally be something like 1 nanometer or something like that. It's quite literally a distance. It's a distance just like any other distance, but it's just a really tiny distance. And you could break a circle up. Let's say this circle has a length of a circumference of a meter. Well, you could break up that 1 meter into a billion little parts, and every one of those parts would be a ds, right? So that's what the ds represents. It's just a tiny little distance, right? And when we do an integral, all we're doing is we're summing up the contribution of what the magnetic field, let's use the same color for that. So we're going to say here, let's make the magnetic field point like this at any location, so that it's always parallel to the path that you're taking, right? And then what we said was that our integral around this loop of b dot ds, we said would be equal to mu naught times the current enclosed. And we said, well, the magnetic field is certainly constant throughout this path, so this entire thing just becomes b multiplied by this kind of the integral of ds, but the integral of ds is just going to be 2 pi times whatever the radius of this system is, right? And this is where we came up with an expression for the magnetic field created by this. You can see that b is equal to mu naught I, the current, divided by 2 pi a. That's what we came up with for the magnetic field surrounding a current, piece of current, right? I'm bringing this back up again because I don't want this to feel too esoteric what we're doing here. What we're doing over here to the left is we're saying, like, similar situation. I've got different values of the magnetic field at these locations, and I've left something out here. What I'm going to do is I'm going to say on the left edge of my circle right here, let's let the magnetic field point like that. Right? The vector symbol's not right. And then when we get over to this side over here, the magnetic field, it's a different value. What it is, I don't know necessarily, but on this side we also say it points up. Okay? On the bottom side, let's assume that the value of the magnetic field is going to point this way, and that value basically is the same value throughout this entire system. And again, I probably didn't need to write that because I already said this is bx, right? And then on the top, we'll say on this side that the magnetic field basically points this way. Let's just move that over there so it's pretty clear what we're talking about here. Okay, but that bx, this is the value, bx prime is the value of the magnetic field all along the top path. Bx is the value of the magnetic field all along the bottom path, so it's basically constant over this small range dx, and then by prime and by. Okay, and the directions they point actually matter. Oh, sorry, I made one mistake here. I made a mistake. Let's see if I can... Oh, no. I don't know if I'm going to be able to erase this properly. There. Oh, I did. Okay. My bad. I actually want to say that the magnetic field along the top is going to have a value that points this way. So that's my Bx prime. Well, the path... Sorry, the path is still going like this. I kind of want to define them positively, because I want to think of these as being positive values for what we're about to do. So I want Bx to point this way, I want Bx prime to point to the right, I want By prime to point up, I want By to point up as well. And that's my picture. And now we're just going to do the exact same thing we did over here on the right. Now I'm going to take this and I'm going to delete it, because we don't really... Oops, we got connected to that somehow. I want to delete this. I don't have to delete it, do I? Let's just move it somewhere. So it'll still show up in the notes in case you guys want to see it. So I want to evaluate the sum of b.ds around this loop, okay? And I'm going to write it out. Hopefully this is easy enough to follow. On the bottom, we're going to start at this location, and we're going to do bx.ds. And ds is dx. So I'm going to say that on that bottom loop, we're going to get... Let's use black for this. I'm going to get, on the bottom of the loop, so this will be bottom, I'm going to get bx multiplied by the length of this side, which is dx. On the right-hand side of the loop, I'm going to get by prime multiplied by the height right here, which is dy. On the top, notice that bx prime points to the right, but the path goes to the left, right? And what we're doing here is a dot product, right? Dot product tells us that we're going to get a negative bx prime times dx here. And on the left-hand side over here, again, because by goes up and the path goes downwards, just keep in mind here, ds is a vector that points this way on this side. And on this side up here, ds was pointing this way. Over here, ds was pointing this way all along the path. When they're opposite to each other, you get a negative sign out of the dot product, right? Because you're doing a cosine of 180. So on the left-hand side of my loop right here, the final piece of this is going to be by multiplied by dy. Does that equation make sense to you guys? And it's bottom, right, and then this term is the top, and then this term is the left side. And I just want to make that a different color so it stands out. Bottom plus right plus top plus left, these are the contributions that we get here. Okay, did that make sense to you guys? Okay, so let's keep that in the back of our minds. Now I want to ask the following question. If I want to express what by prime is, I would argue, and we did something like this last time we met, which would have been, what, Thursday? So it's been 5 days, and maybe once. I'm going to argue that I can take, if I want to find the value of by prime, that it should be equal to the value of by, over on the left-hand side, plus whatever change in by that occurs over this distance in the bottom, right? So if I take by and I add to that the partial derivative of by with respect to x, and then I multiply by dx, then I'm then going to get by prime. Because this expresses the value here plus whatever the change is times the distance, right? The change is the del by del x, the rate at which by is changing with respect to the x coordinate, right? You multiply that by the change in x, you get by prime, right? If this is too hard to understand, it's equivalent to saying by plus by delta over delta x times delta x. Okay? And that basically simplifies down to by plus delta by, right? That's literally all we're doing, and saying that that's equal to by prime. Whatever the change in b is, You take the value on the left plus the change, you get the new value, right? Hopefully does that make sense to you guys? So that this right here becomes what we can replace Vy prime with. And I'll stop for a second. Do you guys have any questions? Like, for example, if By was 2 Tesla and delta By was 0.01 Tesla, By prime would be 2.01 Tesla, right? I hope that should be easier to understand. I hope maybe I'm simplifying it too much, but does anyone have any questions? No. No. Not constant. No. No. Yeah, this change right here. No. It could be changing in a constant way. It's possible that it's changing in a constant way, but I was just, in general, it's not necessarily changing in a constant way now. Does that answer your question? Okay. Now, you guys tell me, hopefully you can see the pattern here. Now suppose that if I know what bx is, and I want to find what bx prime is, I would argue we can do it basically the exact same thing. I can say bx prime should be equal to the value of bx on the bottom plus the rate at which that changes. And now look at what we did here. It's the rate at which the x component of the magnetic field, the rate at which it changes with respect to y now. Because we're going up in the y direction, right? This is your dy. Right? So you're going up in that y direction. So you need to take the rate of change of the x. This is it's kind of weird to understand. The rate at which the x component changes with respect to y. Okay? And then I could say all the same things about this, but I think you get the idea, hopefully. Oops. Draw. Black. What is this? I don't know what this is. So this now becomes our value for dx and our value for dy, but we're gonna plug those into there and there, basically. Okay. Now I'm gonna erase this stuff so we can continue with the derivation here on the top. This is gonna get a little messy, so hopefully you guys can follow along. I want to say one other thing. I want to step aside and just say one other thing about what I just wrote down right here. In general, you can see what the value of b is, right? I want to also mention that ds happens to also be equal to something like dx times I hat plus dy times j hat plus ... How many ever dimensions you happen to have. Okay, so we have 3 here, so it's just dz times k hat, right? I hope you can see that if I take the dot product of this expression with this expression here, which is essentially what we're doing, I'm going to get bx times dx, right? But I'm not going to get bx times dy. Because I have to do a dot product, and a dot product tells me that when I do a dot product, I'm just going to get the components that are parallel to each other. So bx is parallel to dx, dy is parallel to dy, and when I do bx I hat dot dx I hat, I get this, right? You don't see any bx dy, you don't see any bx dz, and the reason for that is just because of the way the dot product works, right? That's why I only said this is bx right here. And I said this was by right here. I don't care about the other components because I'm doing a dot product. Do you guys see that? The other components don't matter. They would go away because you're doing a dot product. All right. So let's evaluate what this is now. So now I'm going to say that if I sum up b.ds around my system, what I'm going to get is I'll leave bx dx here, okay? But I want to look at that term right there. Negative bx prime dx is going to be something like negative of this thing here, b sub x plus del x component of magnetic field with respect to y. So that's the partial derivative. But then that's multiplied by dx, right? And that's plus the first term here, bx dx. Plus stuff with y. I don't want to write the y term out here because you're going to see that You know what? I probably should, actually. I really probably should. I don't want to confuse you guys too much. So plus the y stuff, okay? Now you see there's a negative on this one now, but that's your by prime. That's the first thing I want to do. So by prime, we'd set down here, was equal to by plus the partial derivative of by with respect to x. And then that's multiplied by dy, right? And then minus this term here, minus by dy. Now you'll notice a few terms exactly cancel out here. That term right there cancels out with that term right there. Can you guys see that? You got by dy and negative by dy. Same thing goes here. Bx dx cancels out with the negative bx dx that shows up in here. And so we end up getting this simple relationship here. That if I take the sum over b dot ds, this happens to be equal to, well, what's left over now? So I've got del bx del y that's negative, and I've got a del by del x that's positive, right? I left something out. Do you guys see what I left out? I left it out right here too, actually. Being sloppy. There should be a dy right here, right? And I left it out right there. Let me see if I can't shift over these terms and make some room here. See how well this works. Nope. Nope. Just want that term. Can I shift those over? Yes. Oh no, I actually did it right the first time. I actually want the parenthesis. My bad. Okay. Grab those guys, shift it over a little bit. There we go. There should have been a dy right here. I'll do it in a different color. That's probably a way of indicating that I made a mistake. And I think there should have been a dx right here. Right there should be a dx. Sorry about that. Yeah. That whole thing there is by prime. Or this is bx prime, right? Bx plus del bx dy. Okay, I think we're good now. Apologize for that. There's so many little subscripts and things that you can mix up here. So what am I left with? I've got a term that is del by del x right here. Let's write that one in. Minus another term that's del bx del y. And both of them happen to have the same term. This is dy dx, dx dy, but you can interchange them, right? I don't think parentheses around that's going to look particularly good. And there's really another way you can write this, actually. This is really... Let's write the whole expression out now. So, this thing that's in parentheses, we're going to talk about what that is. But dy dx, what is that equal to? What would you call that? Yep, it's like the area of our little loop, right? What's this thing? Do you notice anything from the notes last week that looked like that, or from your knowledge of other math classes? What is that little piece right there? By the way, this is the x-axis, the y-axis. This is the z-axis, I forgot to say. Positive z over here, and then negative z back here. A cross product. It's like a cross product. It's not exactly a cross product. Or it's a cross product between what? What does that look like? It says, take the partial derivative of the y component of your vector field with respect to x minus the partial derivative of the x component with respect to y. What is that? Think about where we're trying to go with all of this. Last time we proved that the divergence of the vector field was related to the charge density. But we also talked about a different operation involving nabla, or the del operator, right? What was that other operation called? Curl. Does this look like curl? You go back and look at your notes, or are you guys even taking notes? I don't know. Go back and look at the notes that I probably uploaded last time. Did I even upload them last week? Go back quite a ways to find out. I should have a notes channel, actually, shouldn't I? I'm gonna go back to the notes from last week. They're right here, and I'm gonna go all the way to the top. Where's curl? There it is, right there. It's called the circulation of a vector field. And I'm just gonna pop it in right here. Is there enough room? Barely. Well, there will be after I close this, probably. So that's the curl right there, right? Oh, I didn't like that. It's really struggling right now. Oh man, this application, it's not having fun. So, I need to move more of this stuff over to the right. How did the colors change on that? I must have clicked a button. Now, like look at the bottom expression here for the curl, and look at that guy right there, right? Do you notice anything that syncs up between those two? I know this is E, right? But which one corresponds to that? Which piece? Is it this piece? Is it this piece? Is it this piece? K-hat component, right? So in a very real way, what you could do is you could say that what we have in parentheses right here, del by del x, see, same thing as minus del bx del y, same thing here. This is basically, if I was to take the curl of my vector field, like that, this is effectively the z component, right? That's what it is. That's the z component of my vector field. The curl of it, at least. Does that make sense? It's the z component of the curl. So by taking this, which is effectively a piece of a line integral, if I do this in the xy plane, if I do b dot ds in the xy plane, what I get is the curl of b, z component. And you can imagine if you did it in the xz plane, if we did this, if we had done our loop in the xz plane, which component of the curl would we have gotten? The y component, right? So you always get the third one, basically, right? Whichever plane your loop is in, if it's xy, you get the z component of curl. If it's xz, you get the y component of curl. Right? And what would xz mean? Xz would mean literally taking some loop back here that was in the xz plane. Though it's awful, but it'd be something more like this. This would be a loop in the xz plane. You go around this way, you go up that way, you come back this way, and you come back down to here. And really, this should be flat, but that would be a loop. And this would give you a curl component that would go up this way. Whereas for us here, our curl component basically ended up coming like out of the page. Okay, so we get the z component of the curl, right? I guess I'll leave that there. Now, what I would say now is let's take this expression here. Let's copy it so I can do some more work with it down here now. So we know that the sum of b dot ds ends up being equal to this, right? But we're really interested in talking about the entire, like, you know, the integral of b dot ds kind of through everything. And what we're going to do to deal with that is say that, suppose that I wanted to sum over all possible loops here, right? I would argue that this entire expression, what it's going to look like is, once I do a full line integral, it's going to end up looking something like this. If I do b dot ds and I don't just look at one plane, right? This was the, what was it? We did the xy plane. If I also do the same thing and I do it over all planes, then I'm going to argue that what shows up on the right-hand side right here, since it's something dA, that this is effectively going to become a double integral, which is going to be a surface integral of the curl of the magnetic field, not just the z component now, but everything. And then we have to take that vector that we get out of that, and we have to dot product it with dA. Because if you think about this, what dA represents, so dA is basically a vector, which in our picture, dA would have basically been like this right here. It would have been coming out of the page, right? right? And that's why, since you get the z component here that's parallel to dA, you can think, oh, well, if it's the curl z dA, that's a scalar. If I want to turn this into a full, like, proper thing, I must be having to do some kind of, like, dot product then, right? And this allows us to reframe what this represents. Okay? It effectively represents the circulation of the magnetic field, the fact that it's going to move in some type of a circular pattern. And the right-hand side represents another way to describe the exact same thing. You can now kind of see that what the curl represents, the curl of B, is basically the circulation per unit area. How much does it go in circles per unit area? That's what curl is. Divergence was flux per unit volume. If you go back and look at what we talked about last time. Curl is circulation per unit area. Okay? Now, the next thing I want to do is think about what this is equal to. I had said above that the integral of b dot ds, right, that we derived, showed us that this was equal to mu naught multiplied by current enclosed, where we talk about conduction current, plus mu naught epsilon naught multiplied by the time rate of change of electric flux. Basically, conduction current plus displacement current. Right? Now, what we can do with this, and I think this is kind of an interesting thing to be able to do here, is I can say that this thing, I enclosed, right? I'm going to come over and say that the current that's enclosed, well, we can write that in a different way. We could write that as basically a surface, and you did this in some of the homework problems you guys had, especially in the lab manual. If I take current density, I'm just going to remind you guys that J is a vector that represents basically the current divided by the area, and we call it current density, okay? We don't use it very much, but it's basically current divided by area. It's a vector, too. And it points kind of perpendicular to the surface. How do I want to put this? Suppose that I've got a wire here, right? And I tell you that it carries some current I in this direction here, and that the end cap has an area A. Now, neither one of these things is technically a vector, although area can be thought of as a vector. But I would say that my current density then, J, would just point in the same direction as the piece of wire that I'm talking about. And if I have a piece of wire that's oriented upwards like this, well, now the current density is going to go upwards, okay? It's the way we can represent current as a vector, is by using current density. So if I wanted to find the actual current, I would just integrate, I would do a surface integral, right? And I guess if I want to be proper about this, we put two integrals here and say it's a surface integral of j dot dA, right? What about flux? How else could I write flux? How else could I write the flux? What's another way that I can write flux? How is flux defined? Electric. Go ahead. What is it? No, this is electric flux now we're talking about here, right? But you're right, it's just going to be the electric field dot product with dA. That's how you calculate flux, right? You do a surface integral like this, right? Let's put it all together. What do we have? Left-hand side of my equation is a surface integral of the curl of the magnetic field dot products with dA. And the right-hand side is this. It's mu naught multiplied by I enclosed, but I enclosed is now equal to double integral over a surface of the current density dot product with dA. Probably the same dA that shows up on the left side, right? Because dA represents basically this thing right here. That's your dA, right? And then we need to add to that plus mu naught multiplied by epsilon naught and then d phi dt. Well, that's just going to be the derivative of flux, and flux, as we see over here, is, again, a double integral over a surface of the electric field's dot products with dA. Alright. Now, the final thing that we can do here is I can say, well, this ddt and this surface integral, as long as the surface isn't changing in time in some way, like if the electric field is really only a function of, what's the way to put this? Since the integral here, the surface integral, is over space, and the derivative here is with respect to time, you can change which way you do this. You can either take the derivative first, or you can take the integral first, right? You can kind of interchange the order of the derivatives here. Now, if this was a spatial derivative, I don't know if you could do that. I think you can in certain circumstances. Like if this was ddy or ddx or something like this. I don't know if you could do this, but I think since it's ddt, you can. As long as the spatial coordinates x, y, and z are not a function of time. I think I'm saying that right, although I'm probably not. But you guys can tell me what you think about that. So what do we have? Well, really, I only need to rewrite one thing real quick here. Now let's do it like this. So left-hand side ends up becoming the surface integral still of the curl of b, okay, dot dA. But the right-hand side now I can write in the following sense. It's basically mu naught multiplied by the surface integral of j dot dA plus epsilon naught multiplied by can you guys see that? The right-hand side has the exact same format for the integral, so I can take the j and I can take the dE dt, and I can basically just put them all in the same integral here. Oh, and I made a mistake, and that must look very confusing. This is a vector, and actually what I want to do is like this. I want to take this piece here and put it right here. Oops. And then I want to move all that stuff over to the left. There we go. I'll erase those other marks there. Okay, but the way I did that was kind of confusing. I hope you can see. Basically, this is an integral with respect to dA. This is an integral with respect to dA. I can push the ddt inside of here so that it becomes dE dt. That's that term. And I pull the dA basically out of both of them, so that you basically just absorb both these things into the same integral. Whew, that was probably too complicated. I could have done that in a way simpler way, but do you guys have any questions about what I just did? I see someone's typing, so I'll give them a chance to finish typing. Yeah, I pretty much just factored it out, yeah. That's all that we've really done. Is just note that, you know, I mean, it's a simple, actually, let me give you an example of what we basically just did. If I had an integral, whoops. If I had an integral of cos x dx plus an integral of, I don't know, natural log of x dx, this is equivalent to the integral of cos x plus ln x dx, with the extra caveat that this one had a ddt in front of it, so we ended up putting a ddt over this one guy too, right? That's really it. That's all we really did. Nothing super special about that. You guys have any problem about that operation of interchanging the derivative with the integral? When we took this derivative basically and we said, oh, we can just basically push that into the integral right here. Did anyone have any problem with that? Are there any mathematicians out there that find that to be problematic? It's okay if so. No? One of these days I want like one of the math professors at our school to sit through my class and just tell me all the things I'm doing that are wrong. Alright, so now what are we left with? What's the next line? You might notice that this is an integral with respect to dA, and this is an integral with respect to dA. And they both are over the same surface, S. So, it should be the case that the integrand, this one, and this one here should be equivalent to each other. And that's the last line of this. If I take the curl of the magnetic field, this is equal to mu naught times the current density plus mu naught epsilon naught multiplied by the time derivative of the electric field. And this is a vector. I should have written it as a vector here. This is the third... Oh, sorry, this is basically the Ampere Maxwell law, you might say it. Okay. It's called the Ampere Maxwell law, right? Yeah, Ampere. The curl of the magnetic field is equal to the current density plus the time rate of change of the electric field. Basically, this tells us that if you have an electric field that's changing in time, you get a magnetic field that has circulation to it, right? A changing electric field produces a circulating magnetic field. Now, there's another derivation we can do with this too. We can kind of skip all the steps now, though, because you've seen how it works. If I start with the other equation, which is Faraday's law, right? Faraday's law tells us that if I find, what does it say? It says that the EMF is equal to the time derivative of the flux, right? But what does that represent? Well, EMF is given by this integral. Oh, there's a negative sign here too, right? It's given by this integral. It's the integral of the electric field dot product with ds. It's a line integral. And the right-hand side of the equation is basically negative ddt of flux, but flux is basically the double integrals over surface of magnetic field dot product with dA. So surface integral of b dot dA. That's what flux is, right? But we just proved, effectively, and there's actually a mathematical theorem, I think it's called Stokes' theorem. It's effectively what we quote proved. We didn't really prove it, so to speak. But we showed that that a line integral of a vector field like this can basically be rewritten as a surface integral as long as you replace your field with the curl of the field. Right? Because this represents circulation of the field, the line integral. And this represents circulation per unit area, right? This is like really similar to when we say like, you know, density equals mass times volume. So if I know the density, and I take density times volume, I get mass. This is like something is circulation per unit area, multiplied by area. And what do I mean by circulation? I mean that magnetic fields are circular. They're circular things. And the amount of circulation is proportional to how big the current is. It's proportional to the size of the electric field and how it's changing. So coming back to this, that means I can rewrite this in accord with this right here. I mean, certainly the mathematics don't care about whether it's a magnetic field or whether it's a electric field. The same thing is true. This integral of E dot ds can also be written as a surface integral of the curl of the electric field. Dot dA. And then my right-hand side of my equation ends up being the surface integral of, and there's a negative sign, dB dt dot dA. And now when you look at the integrands here, they're both the same. They're both with respect to this dB dt and this thing over here are the same. There's a negative sign, so you basically end up saying the curl of the electric field, which represents the circulation per unit area, is equal to the time derivative with a negative sign of the magnetic field. That's Faraday's law. What it says is that a magnetic field that changes in time produces the curl of an electric field. That's to say, an electric field that's circular in nature, right? What's a really good example of this? Well, a really good example of this is a solenoid. Right, a solenoid is something where you have wire, And then you take a magnet, right? You take your magnet, and you say, what do I need to do to make this magnetic field change in time? Well, one thing I can do is to just push the magnet into the wires. What does that do? It literally makes an electric field in the wires that causes a curl, which is to say it basically forces the charges to move in a circle, because there's an electric field that's produced inside of here. There's an electric field that's produced inside of here too. And it's a circulating electric field that goes around in a circle like this, and little charges get pushed by it, right? You create a force inside the wire because you change the magnetic field. You push it this way, it's changing in time, right? At first it's small, then it becomes big, right? And what does that do? It makes things go in circles. That's what curl means. Curl means things curl, right? They have circulation. Now, it's not just everything being equal, because if I were to take a bigger wire and wrap it around this, the area is larger, so the curl is kind of diminished in some way. And maybe the current's diminished in some way. Or maybe it's increased, depending on how fast you change this. All right, so, you look at those two equations, right? And when we put all of Maxwell's equations together, what we have basically is the one we derived last time. What's it doing? It's doing that thing again. My favorite thing with OneNote. So we're gonna reopen it. The other two equations were, let's put them like this. One of the equations was basically the divergence of the electric field is equal to a constant, rho over epsilon naught, and the one for the magnetic field is the divergence of the magnetic field is equal to 0, because there's no such thing as a magnetic monopole. Those four equations are Maxwell's equations in differential form. And what they tell us is that these two over here describe electric and magnetostatics. The ones on the right tell us what happens when they change in time, right? You see the similarities here? It's like Ampere Maxwell says time-changing electric field produces a circulating magnetic field, and this one says a time-changing magnetic field produces a circulating electric field. The other two talk about divergence, which describes the way in which the field kind of grows from a location. The flux per unit area, or volume. And those are Maxwell's equations. You guys have any questions? I mean, I guess it depends on the situation you're looking at and how you want to describe what's happening. There's probably going to be situations in which this is an easier way to describe it. Depending on how you want to understand a magnetic or electric field, these might just be better ways to look at them. I can tell you, all I can do is talk about my own experience, right? And in my experience, I spent a lot more time using these versions here. I think. Yeah, almost certainly. Because I was working on a project when I first started grad school. I was in an optics laboratory where what we were doing is we were taking fiber optic cables and we were investigating how we could use... So we'd take a fiber optic cable and basically trim it down, so to speak, until it came to a little ball and produced a tiny little sphere that we called a microsphere. And we would use this little microsphere. I guess I can draw a picture of it. So what I would have in the work that I did, and this will get back to what we're talking about here, is you basically had a fiber optic cable, and then we took a piece of the same cable, which is made of plastic or something like this, and we basically took that cable and we shaved it down until it was basically like a tiny little wire, and at the end it had a little tiny circle, and we called that a microsphere. All this stuff made of plastic, right? And then within the wire, there was a light wave that was going through here, right? So you imagine there's light that's traveling through your fiber optic cable right here, kind of bouncing off the walls and stuff like that. Now, I'm jumping into light because this is what we're talking about next, but what I'm going to tell you right now, as I have before, the fact that magnetic and electric fields can oscillate in time and interact with each other means that light itself is an electromagnetic wave. And when you're describing the properties of this electromagnetic wave, one of the things that it has as a property is there's kind of some, what we call evanescent wave that kind of leaks out, you might say. And this wave can kind of like leak out a little bit, and what it can do is it can basically get caught inside this sphere, okay? And then the sphere basically can resonate and absorb some of the field, all right? And when we were describing the mathematics of how this would work, our goal was to figure out how to make this more efficient. And what this microsphere was is it was basically a sensor, okay? And it could be used to detect information about this fiber optic cable. But when we were describing the wave that would actually propagate into it, I remember that we used these equations. And we used Mathematica, and we would solve for the values of the electromagnetic fields by simultaneously solving, well, I guess this equation and this equation here, basically, because this was a field that was changing in time, so you need to describe it by those two equations. We didn't use the curl versions. And I think part of it was because I remember asking the guy at the time, why didn't we use these other Maxwell equations? And he said Mathematica was just better at handling them this way. It was more efficient at solving for the values of the electromagnetic fields if we used the integral form. So Mathematica at the time it worked better in describing the system to use the integral forms, okay? But then I remember later on in school, we were talking about electromagnetic waves and we used the other forms. Specifically, I remember when we were talking about lasers. Now, we're getting very much into details that it's been so long that I don't particularly remember, but I remember when we were talking about lasers that we used these two things to describe what was happening inside of a laser. So, that's not, I don't know if that's the best answer you want to hear, but it's just my experience. It's kind of all I can go off of. Does that answer your question? That's cool. All right. This is a really interesting project too. I remember what I found fascinating about it was it really convinced me how computers are still very powerful at solving problems. This is back in 2005. We would set up these Mathematica notebooks to calculate things and to solve for values and look for optimizations that we could do. And when I ran the program, it would literally take 24 hours to run. Like, I would start it before I went to bed, or I'd start it like when I left work, and it wouldn't be done for like a couple days, basically. And like literally all it was doing was solving these equations. It's quite fascinating, to be honest. This is good computers too. They're powerful computers. We were quite literally running on a cluster. If you guys know what that is, a Linux cluster of like really, really fast. Yeah, and we just needed it. It would still take 24 hours on that cluster. It was insane. Just doing calculations, just running them. Anyway, so those are Maxwell's laws in differential form. Next time you ever on campus again, you go and you look at the top of the board in Physics 1C, you'll see all of these written out. And it says something like, Maxwell said this, and then at the bottom it says, and then there was light. It's kind of this like joke about Genesis and the fact that they produce light, basically a light wave. All right, this feels like a really good place to take a break. I'm going to